suggestion. Good. Right. Well, thank you very much. Thank you very much, Ellen and Cornelia, for your contributions. We're going to move on to the next talk now. So it is A.Lombardi and D.Oustale. And so if you have yeah, this one microphone there. And the pointer, that's right. That's right. All right. So the question, yes, that they're asking is it possible to produce semi-rigid trays using PHBV? Thank you.
Okay, we will try to answer to this question together with David and Luigi, that have the next presentation after mine. My name is A.Lombardi. I work for Coopbox in the Research and Development Department. Our role inside the Glopack was as a Work Package 3 leader, and we were involved also in Work Package 2 and Work Package 4 in different tasks. One of our objectives inside the project was also to use the material extruded by Fraunhofer to produce thermoforming trays. In the project, the main two technologies used for produce food packaging, let's say, was thermoforming trays, so the thermoforming process that was up to Coopbox, and the injection molded cups by FurstPlast that will be presented later. The thermoforming process, that is here, there is a scheme of that, usually consists in the processing of rolls of material, typically standard material like PT and PS. This sheet of material, these rolls are heated in an oven so that material becomes more soft and it's possible to thermoform it. Thermoform it means that you have to use a mold to give the final shape of the material so that you have the tray. And after that, you have a cutting station so that the single tray is separated by the total foil, so that you will have the single tray that after is the production of that. Okay, in the industrial process, usually there are different steps. The first one is the extrusion of foil, like Cornelia before explained. The extrusion at the industrial scale usually is made on machines that are able to produce also typically 1 ton of material per hour, so with a very high output. These materials, the rolls, as we say, typically of PT, PS, or PP material, after are processed on thermoform machines that are able to consume 100 kilograms of material per hour, and the output is around 10 or 20,000 trays per hour. So you have to consider that it's quite high quantity, but it's the industrial part. Since the quantity of material involved in the Glopack project was lower than that, we decided to move to a laboratory scale machine that was able to thermoform the sheet provided by Fraunhofer. Here you can see the comparison. On the left there is a standard thermoform machine with a high production with a lot of cavities in the mold. It's around 20 or 24, so you can produce 24 trays every time, every cycle. On the right, there is the lab scale that is able to produce 1 tray per time with a lot of manual work, because you have to heat up the material after making the thermoforming and after remove the part that is formed, after cutting by hands or by some semi-automatic system. And the output on the laboratory scale is around 5 minutes per tray. So the comparison is quite clear. But with that machine, we were able to process a sheet of the dimension of A4 foil. So it was more suitable for the user for the project. We decided to schedule the trials the thermoforming trials in different steps. We didn't have a very high knowledge about the PHA materials because it's not a standard commercial material used for food packaging. So we decided to go on in different steps. The first step was to obtain some knowledge about this material. So we started transforming and thermoforming some commercial sheet that was on the market, that was made by some PHA with a medium chain length. These materials are not coming from food waste, but are coming from some selected feedstocks like sugars or plant oils. So it's something commercial, and it's quite different from the material that we want to use inside our project. So the material coming from food waste, like the one provided by Innovent and others. The results in thermoforming with this commercial sheet were quite good. It was possible to thermoform it in an easy way, let's say. The result was quite homogeneous, and this was the first point to have also some knowledge and also to adjust our machine to do the thermoforming. The second step was to start using the material that was extruded by Fraunhofer using some commercial PHBV grades. Different grades were tested, like was explained in the previous presentation. Different grades also with different thickness, because thickness is quite important to have a good results on the tray. As you can see in the picture, results were very different. We had very variable results. In some cases, we can get quite well-formed trays, like in the case of PHI003 and also in the case of P209E grade. The color is slightly different, but the final result was quite good. These grades have different content of HV, from something from 0 to 5. You can see that it was not so easy to find the right parameters and also the right composition to have a good final solution on tray. So after that, we start working also on the mold, because the mold for the thermoforming machine, for the laboratory thermoforming machine, we started using some 3D printed mold made by plastic. The first plastic we used was ABS, but we find out that since the temperature of the forming is quite high and also the time is quite high, the problem was also that the mold became soft, so it started melting also the mold. So we started with the ABS. After we switched to nylon, that was a little more resistant to the heat. But in the end, we switched to aluminum because this was the only material that was able to give us a good thermoformability of the tray without any problem, without any degradation, let's say, of the mold. Also, we changed something about the machine to improve also the stretching of the material, because the material is not so easy to stretch. So we decided to have also some modification to improve that. After that, after the first test, we produced also trays that were used after for the shelf life test. We found different issues on the thermoforming of these PHBV commercial material. The first one that was also said before, it's a very narrow working window. This means that working window in thermoforming, usually you can work on time and temperature. But if you go outside the good working window, that is very narrow, you can have two problems. If you are work with low time and also low temperature, the material is not stretchable, so you are not able to thermoform. If you go too high with the temperature, the material becomes liquid, so it's not also possible to thermoform it because it's not more solid. And for this material, this working windows, this processing windows is very narrow. It's not easy to find the good. It's not easy to find the good condition. We made a comparison with the PET, that it's a common material used for thermoforming of the trays. So you can see we have a very high forming time, half minute, 30 seconds more or less. We have high temperature, and also, and this means that after, if you want to put this material in an industrial production, you have a very low speed of production, and also a very high consumption of energy, because you have to use higher temperature. Also, we had some cutting problems because the material was brittle. Cutting problems means that after you thermoform the trays, you have to cut to have a good edge, so that after it's possible to use it in the sealing machine. Since the material is a little too brittle in the cutting, you can have some small particles that are detaching, and the edge is not so nice. And this is a problem also during the sealing process, because they are trays for food, so they don't have to release particles and things like that. Another issue that we found was about the aging problems. This material, also the different grades that we get from Fraunhofer, has the problem of aging. It means that after 2 months, the material was not possible to use it anymore, because it became more brittle than before, and also was not possible to stretch it during thermoforming. And 2 months, it's quite a short period. Also, the storage of this material was made at lower temperature, at 15 degrees, so to avoid the aging, or to have it slower. But 2 months was the maximum time that we were able to use it. In comparison, for a standard material, you can use it standard material, standard PET sheet after 4 or 5 years without any problem. So this is something that has to be considered for this material. As a third step, there was the thermoforming of material produced by IVET and extruded by Fraunhofer. In this case, the thermoforming tests were not made in Coopbox, because the quantity of the material was not so high, and in the testing, in the extrusion test that were made in Fraunhofer, it was not possible to find the right parameters of the extrusion. So only a small quantity was extruded, and it was decided to have some very, let's say, preliminary test of thermoforming directly in Fraunhofer. The results are not so bad, because the flexibility was quite better than the commercial PHBV. The only thing is that the quantity was too low to have a clear result. This is something that must be investigated when it will be possible to have higher quantity, so that the extrusion can be set in a proper way, and after also the thermoforming. If we speak about the TRL for the process, for the thermoforming process, we can consider that the current state for the Glopack material is a little lower, only because we didn't have the time or the possibility to make some thermoforming test with that material. So on the scale of readiness, it's lower. If we make a comparison with the PHBV commercial material, we can say that we were able to produce trays, so the level is higher. Not an industrial scale, was made in laboratory, but after that we were able to use these trays also for the shelf life test. So the total readiness level is higher. We have to consider what are the next steps to improve the thermoforming part. Improve means to be able to go from the laboratory scale to an industrial or semi-industrial scale. Maybe we will not be able to have the same output as the standard material, but we want to be closer than that. Okay, so to have a semi-industrial production. The main issues are the flexibility. So it means that if the foil is too rigid or too brittle, this is a problem. This is a problem not only for the thermoforming itself, but also for the processability inside the thermoforming machine. Because inside the thermoforming machine, usually the material has to go through different parts and has to be flexible. Otherwise, it will break, so that it's not usable if the foil is too brittle or too rigid. The commercial sheet that we used at the beginning was quite flexible. So it's something that we have to work on it to improve, to have a better production, let's say, to scale up the production. Another issue is the homogeneity of the products of the sheet. The homogeneity is considered in two different definitions, let's say. The first one is that the thickness of the foil has to be even on the all white, because in this way all the trays that are produced have the same characteristic, the same thickness and so on. And it's something that is needed for the industrial process to have a good distribution of the material inside the sheet and also inside the trays. And the other point is that the absence of particles that have some different characteristics, let's say unmelted particles or something like that, because in this way the tray that is produced from this part of the foil will have some problem, maybe some holes or something, some defects. So this is something that should be considered when we want to go to an industrial scale. As a comparison, the commercial material on standard like PTA and PP, the variation of foil thickness is plus minus 5%. This is something that is generally accepted as a maximum. So this is something that we have to consider if we want to scale up the production. Last one that we already mentioned is about the aging problem. The aging problem for an industrial application is something quite, let's say, complicated, because if you buy some material, it's not possible to consider that you have to use it or to store it at maximum for 2 months. It's a short, very short time. And also the problem is that not only on the sheet, but also on the produced trays. So the aging problem is something that should be solved to improve the processability of the material. For thermoforming, I finished. I think the next will be David from FurstPlast. Right. And all the questions will be
all questions over the end. That's fine. Yes, exactly.
Thank you very much.
Your slides carry straight on to the
Hello, I am D.Oustale from FurstPlast. I'm going to talk to you about injection processability. So we are a partner of Work Package 2, and the FurstPlast objectives are to check the suitability of industrialization with the process of transformation of developed pellets by injection molding. We provide the necessary equipment to perform the test: injection press, mold, dryers, etc. So this is a little animation GIF. This is the injection machine, injection press. And in orange, this is the material. So the pellets are melted and then injected inside the mold. And at the end, you can see the final packaging which is injected. It can be a tray, a cup, or a drum. So we need a mold in steel for the cup with the design wanted. We install the mold on a specific machine, the injection molding press. The material, in the form of pellets, is heated inside the plastification screw. The rotation of the screw with temperature will melt the material. And then the molten material is injected inside the mold under high pressure. In this step, that ensures the mold is fully filled. We need to coat the mold with water around 40 degrees for polypropylene in order to solidify the material. And then the molded cup is ejected from the mold. And the cup is taken by a robot. So these are the pellets. This is one of our injection press. This is our stacking by the robot. And this is the cup we inject for the solid design for fresh sheets. The wall thickness is around 1.55 millimeters. So is it possible to produce trays using PHBV by injection? Yes, but like my colleagues. So this is the table with the reference. Here is our polypropylene. So you can see the main parameters and properties. Polypropylene injection is easy. Pressure is correct, not too high. The demolding is easy with air. We inject with a cylinder temperature 240 degrees and the cold mold. And the cooling time very short. And finally, the packaging is flexible. Here is the commercial grade from Thailand. Difficult injection because pressure is high. The demolding is okay. The temperature of the cylinder is lower than polypropylene. And we need a mold with temperature of 15 degrees. Cooling time is higher than polypropylene, but not too high, 5 seconds. And finally, the cup is breakable, too breakable for correct using. So here, this is the result for the high bed compound. Injection was okay because it was one of the parameters they work to have a net flow index as close to polypropylene. So this is a good point. But for demolding, it was not okay because the cup sticks to the mold because of some of component or global properties. And the bottom of the cup breaks during air blowing. temperature is lower too, as explained, Hélène, it's normal. But cooling time is very high, 60 seconds. And finally, it is very brittle and no cohesive at all. Because crystallization during cooling is very high. During this project, we have tested two compounds made from commercial PHBV from Thailand, mixed with several fillers, wood fillers, and cellulose fillers, around 20% of fillers. For the reason is to reduce the cost, and for marketing too, marketing reason. Injection was okay. Pressure little bit high. Demolding with wood filler not okay because cup sticks to the mold. So we need to demold not automatically, but we can demold by hand. And finally, the cup was breakable, too. And with cellulose fiber, it was processability was better, demolding was okay, but too breakable too. We test to compound with 2% of antimicrobial agent, but material was too liquid, and we obtain not good processability, variation of the pressure, because the material is degraded quickly inside the cylinder. So it's not representative of a normal injection, but we obtain cups for analysis. The major progress made, so the injection with lower pressure than commercial one with the last compound from IBET. The problems, we need to dry the pellets for PHBV. We don't need that for polypropylene. We need to use hot mud. PHBV material is more sensitive to degradation into the hot cylinder. The material has a low crystallization time, and so the cycling time is higher. So for summarize, technically, processability of PHBV is feasible by injection, but for that we need a correct fluidity of the grain. So the main flow index need to be as the last compound we test, for example, because the pressure is a good value. We need to have a minimum stiffness in order to support the process, because we need that for good demolding. We can have an objective of flexible modulus of 2000 MPa. And we need to have a crystallization time not too long for shortest cooling time and an interesting industrial performance, of course. That's all. Thank you.
Thank you, David, very much for that interesting talk. Well, we have the third part of the talk. So this is H.Verherbrugghen. So we have a few slides there.
Yeah.
Good, wonderful.
Good morning, everybody. I'm H.Verherbrugghen. I'm project manager in Pack for Food. Just to shortly introduce to you who is Pack for Food. We are a collaboration platform, a consortium of industry partners, research institutions, and independent organization in the whole value chain of food packaging processes. And what our mission is, we try to decrease food losses and food waste, so to contain food as long as possible by packing correctly. Our role in this project, we were leader of Work Packet 4, and we were also actively involved in all the other work packages. But mainly about Work Packet 4, the objectives were to evaluate and quantify the shelf life increase with the newly developed Glopack packages for a selection of dairy, fresh meat, and ready-to-eat food. To qualify the related food and packaging loss decrease for each of these cases, and to assess the environmental performance of each food packaging system as a whole of the entire food chain. Our activity focus was then actually mainly the operational implementation of the newly developed packaging concept with the participating partners, the coordination of the food shelf life tests, and defining in close collaboration with the industry partners and the research institutions of the Glopack consortium the requirements of the bio-based trays to be used as food packaging, which has been translated in the Glopack best practices guidelines. Now, my part here is to assess, is it possible to produce the semi-rigid trays using PHBV? Well, to first show you how a production line really is packing the food after you have seen the injection molding process and the thermoforming process. I think it's interesting to also see how at the end these packages are used online in the industry. This small YouTube movie has been kindly provided to us by our partner Coopbox. This is an industrial packing line for beef. As you can see, the beef is at the start of the line being put into the trays manually. And then in a second stage, you see that the packages are being sealed under modified atmosphere to keep the beef fresh all the time. This packaging machine is doing 4 packages at a time, and the target speed will provide at the end 40 to 48 packages per minute. And at the end of the line, you see that the packages are still going to a metal detector and then are ready to be labeled automatically. And we put in a reusable plastic crate to be distributed to the retailers. So in general, what is important in an industrial packing line, packing production line, of course, safety for the operators, but also for the consumers at the end. So there can be no foreign bodies inside your food packaging, as well as no chips, no metal parts, anything like that. So also no broken cups or trays. Also for a line, it's important to be reliable. The reliability of the production lines I cannot share because that's confidential of the companies, of course. The production speed is important. For beef, for instance, it was 40 to 48 trays a minute. Falafel, which is another case, was 22 trays per minute, because their production is still semi-automatic. And the fresh cheese is fully automatic, is 20 cups per minute. Of course, quality of the final packed product is very important at the end of the day. It should be correctly filled and sealed, and there should be no leakage in case the package is under modified atmosphere, and of course clean. Here you see an overview of the tests we have done with the thermoformed trays and injection molded cups. Both Colruyt and La Vie Belle are using PET trays. So the first two columns are their current packages and how they behave on their packing lines. And then versus the Glopack trays, as mentioned before, we didn't have that many, so we used them carefully and packed them on the sealing machine at the University of Ghent for doing the shelf life tests. The biggest difference here is you see the sealing time, which is up to 3 times more for the thermoform tray, but the temperature is about the same. The injection molded cup, the company Soledad of the fresh cheese, today they are packing at 180 degrees at 0.6 seconds, which was different for the Glopack cups. They packed also on their manual pilot machine. And that was done at 230 degrees, which is about 30% higher temperature. And yeah, the sealing time was about the same. Of course, why was this done on pilot machines? Because today, as you have seen in previous presentations, there is a high brittleness of the current PHBV cup versus the current PP cups that are used for with Soledad, for instance, but we see the same thing for the PET trays. And this is something which is compromising the safety of the food product, because you can't afford having any chips in the trays today. Also, sealing was not very easy. Because today the thermoforming process is not yet in control with the Glopack material because of the unevenness of the initial sheets. The thermoforming, this is translated when you thermoform the trays. In the sealing itself, you have an uneven seal, which makes it a higher risk when you pack under modified atmosphere, that you could have micro leakages. You see the falafel. So a conclusion, yes, we can make semi-rigid PHBV trays. However, today, the thermoforming process is not yet in control, which impacts the sealing, and because of the uneven sealing rim. Also the aging of the PHBV packaging material, which impacts the stock keeping, also for the retailer or the food producer when they want to have some stock of the material before packing it online. And the most important thing today is, of course, the brittleness, the stiffness, the strength of the material in general, which impacts the packing reliability and safety of the consumer. So what needs to be true to be able to pack PHBV trays and cups online in the future? The mechanical process characteristics need to meet the current packaging performance characteristics to be able to pack it industrial and online, especially looking at the robustness, the flexibility. So you need to prevent or avoid or eliminate actually breakage, tears, or chips. So this brittleness, for instance, maybe we could look in the next step to add biodegradable plasticizers. And also we have seen with fresh cheese that some of the food products need a very opaque cup, or even no light transmission can be, where you have even no light transmission. So there we might need to assess adding biodegradable master batch, which might impact, of course, also the production processes. Thank you, and thank you to all partners.